Started. We're going on a journey. I'd like to take you with me on that. Come on, we're in Florida. We're in Florida. You can imagine yourself on a vacation trip, right? Y'all should be smiling. I don't see enough smiles out there. We're going on a journey, okay? And I want you to come along with me. Starting on a journey, it's always good to start with a smile. But we need to think about that journey, right? And the journey I want to take you on is the journey about feeding 10 billion people. Sometimes when people talk about this, it seems about as much fun as a forced march across the Sahara, right? Who'd want to do that? But our goal really is to feed the 10 billion, and it's a joyful journey. At least I've found it to be so. And so let's make it fun, right? Or at least let's make it look like it's fun on Twitter, right? We can do that. Do that at least. So we're going on a journey, and when you go on a journey, you need three things. At least I think we need three things. Number one, take people along with you that you like. This is so important. Take people that you like. That is the prerequisite for having fun, right? So I like you all, so you can come along with me if you want. Number two, be clear about where we're going, right? If you're going on a journey, you want to know where you're going. Because number three, we need to know something about that journey and what we want to do on that journey. But we also need to leave room for happy surprises and interesting shortcuts. This third point is really central to my talk. In my experience, if we fine map things too finely, like every single darn step we take, we become too invested in the process over goal. So as a result, we miss being more effective, right? We need to stay focused on the goal, keep the process in mind, but not be overruled by it. So, number one, bring people you like on the journey. Number two, be clear about the goal, where we're going. And number three, plan, but don't overplan the journey. Okay, very good. So, let's start with number two. We'll get to number one at the end of the talk. But let's start with number two. Where are we going? The goal is very clear. We have a vocation to feed the 10 billion. When I was in graduate school, Norman Borlaug came to visit, and he told me I had a vocation to feed the 10 billion. I believed him. Later, I learned that he told all the graduate students that. But I believed him, and it was true for all of them, too. I'll tell you the same thing. You have a vocation to feed the 10 billion. We need to increase our wheat and barley supply by about 50% to do that between now and 2025. To meet that goal, our rate of yield improvement needs to increase by about 1/3. That's a bunch. We can do it. We have done it in the past, but we haven't seen those rates of increase for at least 30 years. Simply achieving that 50% increase, I'll have to say, is relatively easy. I know, it sounds easy, right? But it's relatively easy. That's not the hard part. The hard part is we also need to reduce carbon dioxide created through our farming practices. We will be required to divert farmland to dedicated environmental purposes. And due to increasing urbanization of our populations, we'll also have fewer people contributing to that success. We will need to be effective and productive with fewer people. There it is, the goal. We need a 50% increase in our rate of productivity. We need to hit environmental targets, and we need to succeed with fewer people. Also, keep in mind why we're here in Tampa, right? The grain also needs to be healthful, functional, and free of mycotoxins, right? It's not enough just to have grain. we're producing food. Grains are a necessary component to a balanced diet. All the rest of that, the 50% increase in productivity, the environmental targets, the resource management, all of that means very little if the grain is not healthful. Is that even possible? What do you think? I see a few, yeah, maybe. I'm going to give you a big head nod, right? Publicized research papers consistently point to a potential yield increase of about 50% just by optimizing our current genetics. Similar numbers are published for crop management, integrating current IPM, crop rotation, scouting, precision ag, disease management. They all have the potential to increase yields by double digits. If you would like to go deeper, I didn't go into a big literature search, but I did put up a citation that'll kind of let you go into some of that literature. So, by 50% has first order and second order challenges. Our first order challenge is that each increment of yield increase is increasingly difficult to achieve. The easy yield gains, they're already done, right? Each next step requires keeping the old gains, adding the new gains, and then optimizing those genetics through the entire crop system, all around that new genetics, without losing the already realized advantages. I know the picture. It's really hard to get all those cats up one tree, right? That's why it takes so hard to get that next increment. As a second order challenge, higher grain yields require additional resources. You can't produce the same grain without adding something to it. Modifications are needed to the crop rotations to realize sustainable yield increases. And this is important. That's part of why we're here. We understand that fusarium head blight is a disease that can be accelerated by our crop rotations and by our sustainability measures like reduced tillage practices. First and second order effects of yield improvement will challenge us. That is our journey. So, number 3. I'll come back to number 1 at the end. Remember, people are important. They're the most important thing. We'll come back to them at the end. But number 3, the journey. Have an approximate plan for the journey, but leave room for happy opportunities. For the journey of feeding the 10 billion to be successful, we need to be effective, and effective means delivering products to the market that actually increase yield, decrease diseases, while meeting environmental sustainability targets. So, how do we deliver more research products into the market, right? This is about delivering to the farm gate. Over the past 11 years in my role at Bayer, previously, and now BSF, I've been part of teams that have evaluated R&D pitches. These are both internal and external research funding proposals. And, if you will, I'd like to make a few generalizations. First, we're all talented. We all generally have very interesting research projects. And really, most of the projects have good probabilities of success given enough funding and enough time. And yet, we didn't fund most of them. Many of the R&D pitches were misaligned on what it would take to bring that product to the market relative to the value it would deliver. The market value of a product did not justify the time and work required to take the idea from its current form to a finished product, right? You all know what this looks like, right? You really do know what this looks like. This is the paper where you read the abstract, and they say, this disease QTL from an exotic source is found. And they conclude that QTL will dramatically help breeders control disease. right? How many times have you read that? Yes, maybe, if. If epistasis does not suppress the disease resistance in an elite background, if it does not have a large yield drag, if it will work in our production environment, if, right? All those are required research phases before that conclusion in the abstract will be true. Intuitively, you know this, right? And so what we need is a tool to align that effort, that intuition, with the potential of that product and what it takes to get it to the farm gate. So we need an alignment tool. So let me explain what this is, right? So you've been looking at this graph for a bit. The alignment tool that I like, it's one that I've been using, and it's one that many R&D organizations use, is really some version of this phase model of research, right? So this is a research phase model. Phase 1 is discovery, the initial idea development and information collection, that QTL that we thought about that was in that paper, right? Phase 2 is a technical proof of concept, making the initial working models and testing the assumptions from the discovery phase. Phase 3 is commercial proof of concept. Can the idea scale to a commercial product? This, again, tests those assumptions from the discovery and the technical proof of concept phase. The fourth phase is development, testing and adjusting the commercial product for the customer. Then the final phase, phase 5, is life cycle management. Once a product hits the market, are there new and better ways of expanding its value to our customers? This happens all the time, say, with fungicide products, right? So I've got this drawn as a circle because in a perfect world, life cycle management, our county agents, for example, they're on the ground with the growers, and they must be providing the raw material that drives the initial discovery phases. In fact, if you think about it, all these phases actually do have to have feedback. There should be circles of circles. So, take a moment and think about it. Where does your research work fit into this phase? Can you place it on the map? Right? Where do you spend most of your time? For example, someone working with alien disease-resistant sources is usually back in discovery and technical proof of concept. Pre-breeding, or IPM development, often fits in the commercial proof of concept or development phases. Breeding elite lines uses established commercial principles, and so really most breeders are working in the development phase or perhaps life cycle phase. Crop extension specialists really are our experts in life cycle management. We need to know and value all the phases of this process. Enabling people to be effective in all these phases of work is critical to increasing our rate of yield gain. We all need to be effective. The U.S. Wheat and Barley Scab Initiative, why I like this organization, this is really almost unique. You work across many different institutions, and normally this would be a barrier to collaboration across research phases. You've all succeeded by being intentional, though, about your collaboration and your information sharing. Do more of that. That's really a key to success. So let me continue to encourage you to build on those strengths. It really is key to being effective. The research phases in this model align expectations. It allows us to respect the works of others and bring products to the market. There will always be surprises and opportunities, yet we kind of need a rough plan. We need to leave room for them in there, but we do need to kind of know where we're going. Competing projects often have different life cycles. They often have different costs, different probabilities of success, and they feed off of each other in a well-designed program like this one. Because we do need a wide portfolio that will provide a range of value to our farmers. And as for those surprises along the journey, they really come from learning from each other. So, let me give you a couple of examples. I want to walk through a few examples. That previous slide was hypothetical, but let me take the circle and stretch it into a line, okay? So, let me use two examples. The first I would like to use is the FHB1 gene. Confers host plant resistance to Fusarium head blight. This is a good example of a project. It really is a nice illustration of this model. More generically, we could talk about using exotic sources for host plant resistance, because it goes along with this. So let me tell you a story. Back about 1990, one afternoon, at the Hotel Costa de Oro in Obregon, Bob Bush, the former breeder at Minnesota, was sadly looking into an empty beer glass. Ed, he says, I know, what could possibly go wrong? Two wheat breeders walk into a bar. But there we are. So Bob Bush and Bob Bush says, Ed, I've got these sources of Fusarium resistance, things like Sumai 3. These things will be a millstone around my neck for the rest of my career and for the career of the unlucky breeder who follows me. How are you working on that, Jim? He's good with it. All right. Bob could be a pessimist because one breeder's millstone is another breeder's success story, right? In the 1980s, breeders were in a discovery phase looking for novel sources of resistance to Fusarium. In the late 1980s, Sumai 3 and similar Chinese lines were used for U.S. crosses. This was moving the resistance from discovery to a technical proof of concept. We wanted to try it out. Those exotic sources of Fusarium resistance started to reach pre-commercial in products such as ND 2710 by the mid-1990s. In this process, the Fusarium resistance was diagnosed as quantitative, a significant QTL was identified, and was placed on 3B. So that's FHB1. So we have a concept of what resistance is, roughly how to use it. The FHB1 resistance was then deployed using phenotyping and later mapped markers. And so this really kicks off the commercial proof of concept phase. The first varieties with resistance from using FHB1 began to appear in the early 2000s. So this is now the development phase. This is when we progress with resistance through normal breeding. So each of these phases took a little less than 5 years to get up to discovery phase. And that's relatively fast for a novel trait, which is good. But here's the basic problem. The development and life cycle phases of breeding vary widely between programs. It is an enormous breeding effort to move a gene from 1% of your breeding program to 50 to 80% of your program, which is what is required to have a sustainable pipeline of resistance. Moving a trait into 1% of your germplasm can give you a successful launch, but the pipeline for serving customers is a target that takes much, much longer. And so really we don't reach the life cycle management or the completion of development phase until a much later date. Today, after 40 years of work on Fusarium, FHB1 is in about half of the Great Plains spring wheats, maybe a lower percentage in the soft winter wheats, and it's in almost none of the hard red winter wheats of the Great Plains. We've made general progress, though, in Fusarium resistance of our varieties across all of the regions. So how did that happen? Life cycle management of regular breeding methods improved native resistance in elite germplasm. The life cycles for breeding method improvement really are much, much shorter than the breeding cycles themselves. We do innovation every year on it. The FHB1 gene has a relatively large effect. But most of us could not justify a similar integration effort for a new alien QTL of similar size. It would just take too long. Also, today we've had fundamental changes in our basic technology. Today, if we started a selection program for fusarium resistance, our preferred method would likely be use of a genomics platform. This is possible because resources that were put into human genetics have outrun our routine technology development, and we've adapted them and now use them for things like fusarium resistance. So let's use that as a comparison. That's a second project, and that is bringing genomics into plant breeding. It's another good example of a phased breeding project. Much of our current genomics is really based on methods that were developed in a much larger field of human genetics, and to a certain extent, corn as well. The sequencing of the human genome was completed in 2003, at least that's when it was published. So let's mark that as the start of discovery phase. Wheat geneticists started working on sequencing the wheat genome. The International Wheat Genome Sequencing Consortium kicked off in 2005, so let's mark that as technical proof of concept. The wheat sequence was completed about 2015, which started a wide range of commercial phase applications. Application of genomic selection is present in wheat breeding programs and barley breeding programs by about 2020. During this current phase of development that we're in now, a wide range of methods are tried and optimized. We're really slipping into what is more of a life cycle management of genomics, right? Many small incremental innovations that happen continuously. That's a fast cycle. It's mind-bending, right? The costs of genotyping have dropped faster than the cost of computing in the comparable time. It's pretty amazing. The integration of exotic germplasm and genomics, genomic development, they're really radical different projects. It's really not fair to compare them, actually. They have different funding, different cycles, but in a way, that's really the point. That's what I want to make. It's a happy surprise, right? Happy surprises and shortcuts happen in the journey, and they're routinely found in these types of mismatches. It's precisely the reason that breeders should listen to the basic biology of the pathogen. Extension educators should track digital phenotyping improvements. They move at different speeds and bring different perspectives. So to wrap this up, on our journey, balance technologies. Deliver values to customers. Do it using a mix of solutions of different phases, different cycle times, and different probabilities of success. But know where you're at in that journey, where you're at in that research phase, and respect all the other people in that phase it's going to take to bring to the product to market. Respecting those people. We'll finish with number one. Take people on a journey that you like. This is really the most important point. People do science. Science doesn't do science. Take people on the journey that you like. Think about it, all the people that are in the phases that precede your work, and all the people that are in the phases that come after your work. Also be aware that in this room, there are many people that are in parallel phases as well. All those people need to succeed as well. Bring them along and help them succeed. So, how do we do that? How do I enable their success? This question really doesn't have a single answer. Every situation is different, but start by liking those people. In my experience, those solutions come more easily if you like them. This may sound a little trite, but liking people in science is different than liking people on Facebook. We like people who do science well. We do. But it's also important to understand we will need a mix of different sciences, which requires a mix of different people. Diverse portfolios of science come from diverse portfolios of people. We need a mix of backgrounds, talents, and experiences, and most importantly, a team commitment. And what I have learned over the years, I need to learn to like them for those traits. Take people along on the journey that you like. Learn to like more people. On our journey this afternoon, we began with the vision of feeding 10 billion people. People who are committed to feeding the 10 billion people, those people, they're the ones you want, right? They're the ones who will plant barley trials on a cloudy, windy day when it's 25 degrees out, and they will like it. Those are the people you want along with you, right? They believe the vision. So one of the things I've found is when hiring people, it's helpful to include the question about sharing the vision. Commitment to a common vision on a team can carry you through many rough places. And there will be rough places on the journey, trust me. They come. And you need to be ready for them, and you need to have a team that's ready for them. Sharing that vision enables that. So, do you believe in the journey? Over the next couple of days, you and your colleagues will make choices. Those choices will determine your likelihood of delivering profitable crops, disease control, products to our farmers that will enable them to feed the 10 billion. Let me encourage you. Choose a mix with each other. Choose a mix of science you believe in, and look closely at how to leverage each other for success. Ask the question when you're looking at this, will this product actually deliver something valuable in the time it's going to take to get it to market? Who else do I need at the table to make it successful? Ask yourself, after I've done all this, how do we help other people see the vision? Because this is going to be a long trip, and we will need company on that trip. Thank you.
Lucky for you, I'm back, but only for one day.
How did I draw the short straw, Carl? I could have talked yesterday.
So I guess where I see what I saw during my career, which was a source of major frustration, was the real limiting factor to basically increasing yield production was not the genetics per se. One, price, input cost, and climate. So in looking at, if you have state yield contests, those yields are probably twice of what you have in your breeding program. The yields that you have in your breeding program are 10 to 20 bushels higher than the state average. And if you take your varieties, for example, soft red winter wheat, send them to Yuma, Arizona or Aberdeen, Idaho, the yields are even triple that. So my frustration is that growers are not even able to capitalize on all of the yield potential that we currently have in our varieties. So my question is, how do we get around and help the growers actually reach more of that yield potential?
Good statement. And what I would say is, going back to my circle, right? When we develop products, we really need to be out there talking to the farmers and getting feedback, right? Ruth mentioned we're working on hybrid wheat. One of the things I like about hybrid wheat is the stability of the yield. That's one of the things we consistently hear from a lot of growers, right? The reliability of wheat. How do we make it more reliable? That's one of the feedback points that came back consistently to us when we did customer surveys. That's one. I just use that as an example. I had to slip that pitch in for hybrid wheat. But I think that's the way we do it, right? We don't make these things up in a laboratory. Well, we do, but we do that after we talk to them and find out what's the gap. Why aren't they using this technology, right? Because there's a lot of technology out there that just doesn't get used. And so the question is, why not? I don't have the answer. Go ask them, right? Deborah's going to follow me. I'm going to make a pitch because she's going to answer that question much better. And she's also a big fan of extension agents, right? So this is good. All right, good, thanks. Ruth, how am I doing for time?
I think we can have one more question if somebody has one.
All the way right over there, I think.
Nice talk, Ed. I have one question. You mentioned that pipeline showing the example of FSB1, right? So identification phase, then discovery, then deployment, and then commercialization phase. So what we can do to cut down that phase when we are putting those traits into the varieties, because there's the identification phase is pretty big, right? So when you find a trait, what should we do in the collaboration with the public programs and private programs to speed that process up?
Yeah. So speeding the process up, this is a really good question, right? And I think it's also at the crux of things. We work with biological organisms that have a set number of cycles. And even if we accelerate the trait integration, we still have to test it a certain number of years in the field. Otherwise, how do we know if it works, right? So we're stuck with that. So my answer is, let's be more effective in the time we have, right? I mean, that's why genomic selection is so interesting. It doesn't necessarily change the cycle time, but it really does accelerate what we can do during that cycle time, right? So that's, I think, the key to us is how do we be more effective with the time we have and find the technology that's going to enable the increase in the rate of gain on that. That would be the way I'd look at it. Thank you, Ruth. Thank you all for the opportunity to talk.